up. Okay. Can everybody see my screen?
Mm-hmm.
Okay. So let's get started then. Hi, everyone. This is the before last semester seminar of the semester, and we are really excited to welcome again one of our very own. So Professor Ryan Martin is a professor of statistics in our department, and he received his PhD in statistics from Purdue University. And before joining our department, he spent 5 years in the Department of Mathematics, Statistics, and Computer Science at the University of Illinois, Chicago. So besides his really impressive work, he is also the co-founder with Harry Crane of Researchers One, which is an online platform that aims to really have everything that is necessary to do good research. So I'm sure that he will talk about it a little bit more. I hope so. And so there's peer review, and you can put your papers there, and you can really engage with your community. And so if you haven't had a chance, I really do encourage you to check it out. So today he is going to talk about imprecise probability and valid statistical inference. So a brief reminder that talks are generally 45 minutes, followed by about 15 minutes of questions and discussions. Please remember to mute yourself unless you have a question. If you do have a question, you can also raise your hand or post your question in the chat box, and I will keep an eye on that. And I will also give our speaker a reminder around 10 minutes and then about 5 minutes left. So with that, feel free to start sharing your screen, all you.
Okay, well, it looks like, I think it's sharing, it's right, it's good. Good, okay, well, yeah, thanks for coming to this. And we mentioned it was second to last seminar, so it's getting getting towards the end, and so people are getting worn out maybe with all these Zoom meetings and things, so thanks for coming to listen in. So I thought I'd better make this sort of a provocative kind of topic here, hopefully get some attention. So, yeah, I'm going to talk today about imprecise probability and how this relates to statistical inference. In case I forget, so I mean, I probably will forget to mention this at the end. I'll have these, they're not there yet, but I'll have the slides there on my website. The link is there. So if you're interested in any of the slides or any of the related materials that I present, you can find that stuff there. And again, I'll also forget to say this at the end, but if you have questions about something either during the talk or maybe afterwards, you want to send me email, I'll be happy to try to answer those questions. So let's get into it. So I mean, sort of my view of, sort of how statistics is a bit different from, other kind of related topics like machine learning and so forth, is that the focus, or our focus, is really on reliable or sort of valid uncertainty quantification. And so the idea is to somehow convert the data and maybe model assumptions into some kind of quantification of the uncertainty about those unknowns. And so in statistics, we have really two dominant kind of schools of thought on this topic. And so everybody knows these are frequentist and Bayesian. I happen to think that the dichotomy between these two things is actually not good for the subject. And so I think in particular, there's some confusion about what's the difference and similarities between them. And in fact, maybe thinking of it in terms of this or this actually masks some kind of hide some opportunities to develop some new ideas. So I like to think of these as kind of two ends of a spectrum. And so then the question obviously is then, what is the spectrum? And so the way I like to think is, well, the more I'm willing to assume, the more precise I can be. And similarly, the less I'm willing to assume, the less precise I can be. And I think that's really not controversial, but there's this sort of key word there, which is precise. And also, if you're talking about more or less precise, there's, I guess, degrees of imprecision. So that's really where this kind of idea about the imprecise probabilities, I think, fits into the statistical problem. So I think that, even though we're talking about a spectrum, and in particular, the frequentist and Bayes are kind of at opposite ends of this spectrum, they shouldn't really require completely different ideas or different theories. That somehow there should be, in some sense, these all go together, and they're the things that make them common are what should stand out, not their differences. So what I want to do is I want to start with some kind of a uncertainty quantification framework, which is sufficiently general, and then see sort of how these different pieces will fit. So what do I mean by that? one of the advantages of a Bayesian type of framework is that everything's about probabilities. So you say, okay, anything that I claim is uncertain to me, I describe that or quantify that with probabilities. So of course, this is not enough, really. I mean, that's not general enough to really capture what the other side of the spectrum would do. And so the natural idea is, well, let's just extend this theory, like the Kolmogorov theory. And well, it's actually too general. So that's actually kind of the key message here, is that there's too much flexibility with general kinds of imprecise probabilities. I'll explain this stuff as we go. And so what we need is actually some kind of a statistical constraints to try to pin this down. So what I want to do here is to talk about sort of what do I mean by sort of this notion of validity or reliability. Then ask the question, okay, well, what kind of mathematical framework is needed? So these imprecise probabilities are too general, and so we need to sort of shed off some of this generality to get to something that's actually workable. And then once we find something that does what we hope it will do, then ask questions about what are the practical, theoretical, and computational implications of this. So this is, I mean, far from being done. I think I have enough to fill an hour with, for sure, so I plan just to tell you about what I know now and what I think is coming up next. So here's the kind of just the sort of outline. I'll give you some setup about the statistical problem and about what I mean by uncertainty quantification. So this is in terms of this kind of objects that I'm calling here inferential models. Then I'll tell you what I mean by this notion of validity, which is what I think kind of fuses all of these different approaches kind of on the same spectrum. And then so there's a couple of main results here, 3 main results. And so I'll give you some idea about these things. So one is that if I focus only on precise probability, then I can't achieve this validity property. The second one is that if I extend myself and say, okay, well, how about some kind of a certain class of imprecise probabilities, then in fact, I can achieve this validity property. And then the third one is kind of going in the opposite direction. It's actually will say that really any kind of a procedure that you can imagine that has these kind of good frequentist properties can be characterized by one of these special types of imprecise probability. So it's kind of in some sense, kind of a characterization of frequentism in terms of these kind of imprecise probabilities. And then I'll say a few words about what does it actually take to construct one of these things. I think there's some interesting things to say there, and then I'll finish with some kind of more general sort of remarks and maybe some open questions. So I think it's not too much time has passed for this to not be relevant anymore, but I do like to call attention. So unfortunately, Don Fraser has passed away. This was the end of last year. Really remarkable career. So it says he was 95 when he passed. I think was still actively working in his 90s. So if we could all have that kind of longevity and productivity, I think that would be really outstanding. So a lot of his work, he didn't speak specifically about imprecise probabilities, but lots of thinking about what does probability mean in these kind of contexts. And one of my favorite papers it's hard to say of all time, but one of my favorite papers is the one that's mentioned there at the bottom about is Bayes just quick and dirty confidence? This is in the Stat Science 2011. So I think a tremendous impact on the field and specifically my way of thinking. So let's get started. So the setup for the statistical inference problem is like this. So I have data that I can observe. It's Y. So here I'm just going to use some generic Y to represent this. It doesn't mean it's one observation. You could think of Y as just the collection of all the things that you've observed. So this bold Y space could be like a product space if you're thinking about like IID observations or something like this. So then I have a model that describes the distribution of these things. That model is characterized by some parameter space. So these are just collections of distributions indexed by points in this big theta space. So I like to do this. I don't know if this is annoying to people, but I like to use this symbol for the actual true value of this parameter, and then some other symbol to distinguish the generic ones from the special ones. So I'll use this other kind of theta. I'll call them both theta, but you can see on the screen that they're different thetas. So I'm going to focus this talk today about the one end of the spectrum, which is the one where I have no prior information. Basically, my prior beliefs are vacuous. Okay, and so then the goal, like I mentioned, is to take the data that I observed, this, let's say, little y, it carries some information about this unknown theta, and I want to use that information to somehow quantify uncertainty about it. So the way I want to think about this is uncertainty quantification means data-dependent belief assignments. So you could think like in terms of, in a Bayesian context, this belief assignment is in terms of a probability, but there's nothing really special about that. So this thing I'm going to call an inferential model, it's just a function that takes the inputs, which are data, model, maybe some other things, and returns to some kind of belief assignments. So these belief assignments are just in the form of a function that takes, here these are like hypotheses about the parameter to number 0, 1. The interpretation here, I'll share a different kind of interpretation in a moment, but the interpretation here is that this describes my degree of belief in truthfulness of this claim that the unknown theta is inside of this set A. Okay, so mathematically these are called capacities, but that's not really so important to us. The main thing is, well, it's more general than probability, but I should first mention that here I am allowing, I mean, I won't really talk about this today, but there's no reason that there couldn't be prior information of some form sitting inside of here, and that's part of the inputs and then therefore would influence the output. So the kind of examples of this, Bayes and fiducial, at least Bayes is probably familiar to everyone. Fiducial, maybe not. Dempsey-Schaeffer, probably even less likely that you've heard of this. So these are kind of, fiducial is well, sort of Fisher's brainchild. And this was meant to be a way of sort of constructing a type of posterior inferences without having prior information. And Dempsey-Schaeffer theory is a sort of extension of fiducial ideas to, I guess, some more general types of problems. By the way, Don Fraser had a number of papers and I guess sort of books related to kind of extending Fisher's fiducial work to other contexts, giving it a bit more of a mathematical framework. Okay, so the main thing I want to focus on here is that capacity, it actually doesn't have to be additive, right? We probably don't really think much about this. Like when we define probabilities, it's very natural to say, okay, well, if this can happen or this can happen, then the probabilities of those two things should sum to 1. So that doesn't actually have to happen. And so there's notions of a non-additive type of let's call them capacities. And so I need to say a little bit about that. So now you get to see some of my art skills. So here I drew these, not freehand, obviously, but so I drew a few pictures here to try to illustrate what I think is kind of the right way or the easiest way to see where this non-additivity type of thing can turn up. So if you think about random sets, so you may not have any real exposure to this, but I think the picture is good enough. So think about this, the red thing is like a random set. It could land anywhere really in this plane. And so then I happen to have this special set here, A, that's fixed. And so you say, well, what can happen when this random set gets dropped into the plane? Well, one possibility is that the random set is completely inside of the A. Another possibility is that it's completely outside. And then of course there's a third one, which is that it's both in and out or neither in nor out. So what does that have to do with the kind of situation we're talking about? I actually define the capacity as a type of a functional of that random set. And so this is usually called the inclusion functional. And so if I define the capacity in this way, then actually because there's 3 possibilities here, in, out, or both, right? Then the sum of these two things, A and A complement, would generally be less than 1. So this is a thing we're talking about here is a non-additive type of a capacity. So actually this random set version is really in my mind, it's really the only way to think about these things. You can do it in different ways, but this is the one that I like the best. And so this doesn't turn up in probability theory is that because everything's additive. But if you're talking about a non-additive thing, there's actually another related function, which is I'm calling here the dual. And it's basically is defined by this kind of relationship. It's not really important for what we want to talk about here. But I do want to mention when you do this kind of definition, then this thing with the lower bar and this thing with the upper bar, there's a relation between them. And that's actually why they have the bars. So the lower bar is to represent sort of like a lower probability or something like that. And then this upper one is like an upper probability. And the interpretation of the this pi upper bar is like describing the plausibility of this hypothesis or assertion about the parameter. Okay, so when I talk about this, the inferential model output, what I'm really saying is that there's a pair. So there's this lower and upper guy. Okay, so now you say, well, what do these things actually mean? Like probabilities, these are things that are subjective. They're like specific to me. I'm the one that constructed this thing. So the way this is usually thought about is in a type of behavioral type of sense. And this usually requires some kind of a gambling type of setup. So you can interpret these lower and upper things as in the same kind of gambling sense. So now there's not just one price that you have for buying and selling, there's two prices. And so these are related to the lower and the upper. So the lower is like the maximum buying price for a gamble that pays $1 if it happened that the theta was in A, and this is my minimum selling price if for that same gamble. So these don't have to be the same. That's where the non-additivity comes from. Right. And so you're maybe familiar with things like about Diffinetti had talked about sort of coherence properties of these kind of things. All that means is that you impose certain kind of constraints on how you assign those beliefs to protect yourself from a sure loss, so to not be a loser in this gamble. So all this is really is like an internal kind of sanity check. So the example I like to think of is that, during election time, we hear a lot about these like, Biden versus Trump, for example. And so then Nate Silver and other folks are saying, well, here's the probability that Biden wins, here's probability that Trump wins. So in order for those things to be coherent, it just means that they have to add up to 1. So anybody can write down 2 numbers that add up to 1. So that can't alone be what it takes for these probabilities to be meaningful. So that is what you need to protect yourself in this sort of internal sense that I'm not going to be a loser, but that doesn't give you any reason to believe the probabilities that I write down. Okay? And so what we need is something else beyond just these kind of coherence properties to make these probabilities or beliefs real world relevant. Okay, so here, when I say more, what do I mean by that? This is where the statistics part comes in. These are statistical constraints. You say, well, what does that mean, statistical constraints? So the way I think about this is that I'm going to write down my degree of belief like this one. So of course, I'll tell you where these numbers come from a bit later, but I have this thing that I'm calling my degree of belief. And so really the only thing I could do with this, the only reasonable thing to do is that if a particular A has I assign a large belief to it, then I'm going to infer A. I'm going to think that that must be a true type of hypothesis. Okay, so that's fine. That's some kind of a procedure that I could apply. So then I like to refer to this quote here from Nancy Reed and David Cox. So it says here that it's unacceptable if procedure of representing uncertain knowledge if used repeatedly, would give systematically misleading results. So this is the constraint, is that I need these belief assignments to somehow protect me from making these mistakes, these systematically misleading conclusions. So what does that mean if I think about it in this way? It says, well, I just don't want to have large belief assigned to false claims, false hypotheses. All right, so what do I have to do to avoid that? Well, an idea would be, how about I add some constraints in how that data gets mapped to this belief assignment? And the constraint that I think makes most sense is like this. It says that if it happens that theta is not in A, and I have a sample of Y from this P theta, then it should be that this belief assignment should tend to be small, right? This is a false claim. I should assign small belief to false claims. Or in other words, if I assign large beliefs to false claims, then I might make mistakes. So I want to try to prevent making the mistakes. So that's, of course, too vague, right? So you have to write down some kind of an actual definition, something that you can work with. So here is my definition of this notion of validity, which is sort of a mathematical explanation of this basic idea that I'm describing here. So it looks like this says that this kind of thing that takes data, models, et cetera, to a belief assignment, this thing is valid if this holds. So the way to think about this is that inside here, so the alpha could be whatever, but think about like an alpha that's small. So this inside of here, this is a situation where the belief assignment is relatively large. 1 minus alpha is now a relatively large number. But it turns out that theta is not in that A. So that means that A is a false assertion. So this is an event that's bad. I'm assigning large belief to a false assertion. And so I want to have some control over that to prevent these systematically misleading conclusions. So that's what validity is doing. It's just protecting you from putting too much belief in things that are not true. Right? And this is something that we actually have to work for. It's not something that comes automatically. I like the version in terms of this like upper thing, plausibility, better, but they're equivalent. So as long as I say for every A, these two things, this one and this one are equivalent. Okay, so this thing about for all A is important, and we'll see that a bit later. It has something to do with that I actually need to protect myself against really any kind of hypothesis that one might want to consider. And you say, well, okay, well, what's sort of the practical implications of this? Well, one is that I mean, we all like our procedures to have these good kind of properties. So if I'm able to construct one of these inferential models to satisfy this property, then I automatically get the familiar type of these kind of frequentist error rate control properties that we all know and care about. So hypothesis test, for example, if I decide to reject a hypothesis, if this plausibility of that hypothesized set is too small, this will have control over type 1 error that's sort of almost obvious from the definition. Right? It's kind of sitting right here in this version of it. Similarly, you can construct a confidence region, or I like to call it a plausibility region. And this one is just a collection of all of those parameter values who are individually assigned a sufficient amount of plausibility. So Brian was talking a couple of weeks ago, Brian Rich was talking a couple of weeks ago about in the context of prediction and using this kind of notion of a kind of plausibility function for those prediction problems. There's nothing special about the prediction problems. This is just a general kind of procedure that one can use and to think about these things in terms of an imprecise probability rather than something sort of that's harder, at least for me, harder to pin down, which is this notion of a confidence interval. What does that actually mean? So in any case, if you construct this guy in this way, then it achieves this kind of nominal coverage probability. So the things that we care about are consequences of the inferential model validity. Okay. And I think that this is actually, it's good both for the frequentist perspective and also for understanding what these inferential model is doing. These are, it helps, at least for me, it helps to explain what the kind of frequentist output is. P-value, confidence intervals, those don't have any like actual meaning. I think that thinking about it in terms of this plausibility actually is helpful. And I'll try to make some more concrete claims about that towards the end. Okay, so now we've got the setup, and so now I haven't really told you anything that's well, it's probably new to you, but I haven't told you anything new yet. So this is I mentioned there were sort of three kind of main results I wanted to talk about. So this is kind of a summary of what those main results are now that we have a little bit of background. So the first one is that if I happen to take that inferential model to be additive, so it's an actual probability, not an imprecise probability, then this validity property doesn't hold. Second is that if I choose this inferential model in a special way, one that takes this upper probability to have this what's called the consonance property, then validity can be achieved. And so this is actually what Brian was talking a few weeks ago about how this conformal prediction turns into these valid prediction intervals is exactly this property, but that was in a different context. So this is a very general type of notion. So I think it's worth to describe that here. And then the third one is sort of a converse to the second one, which says, this basically says that if you pick this upper probabilities or this inferential model in this certain way, then you can achieve validity, and then you can also achieve these kind of nice frequentist properties. This one says the other way. It says, if you give me something that has these frequentist error rate control properties, then there's one of these valid inferential models sitting there behind the scenes. Okay, so somehow it provides a sort of a characterization of frequentism in terms of these imprecise probabilities. So I wanted to give this some kind of, I mean, this is pretty high level, but at least maybe make some kind of practical connections here. So I actually learned about this problem from one of my collaborators, Michael Balch. So I told him about the seminar. I think he's here. So I actually learned about this problem, satellite conjunction analysis, from him. So that's really his domain. And so the setup is like this. It says, well, if you have some orbiting satellite, of course, those things are out there and in space helping us with our cell phones and not getting lost. So these things are out there. And of course, there's no guarantee that they couldn't run into one another or maybe to some other kind of objects. And so this would be bad. So, that's a very expensive thing to do, to get a satellite up into the space. And then if something happened, it's even more expensive to try to do something about it. So they have lots of people working around the clock to monitor the satellites to make sure these things don't happen. And so what they do is they will, I imagine sort of it like when you watch the movies about NASA shuttle launches, they're all at there's all these desks sitting there and looking up at a giant screen. I don't know if that's what they really do. Maybe Michael knows. But so the analysts are all sitting there and they collect data sort of all the time, and then they're computing these things, what they're calling non-collision probabilities. I'm not going to tell you anything about those calculations. If you wanted to see, we have a paper here. You can see some more of those details. So then what do they do with those non-collision probabilities? They say, well, okay, if non-collision probability is high, that's a suggestion that the satellite is safe. So then they just let it be. Okay. So there's an interesting thing that's been noticed in this context. So this is not anything that I discovered or Michael. This was something that was known for some time. There's a thing called probability dilution. And so that's this point here that's sort of emphasized, says that when the data are noisier, the non-collision probability just simply tends to be large. So in these problems, you can imagine, right, these satellites are really far away and they're moving. And so it's hard to make these measurements precisely. So the noisy data is the norm. Okay, and so what I have here is a picture of, these are sort of a toy setup just for illustration, but it is exactly the phenomenon that's going on in these actual non-collision probability calculations. So what I have here is 4 scenarios: the close, kind of far, far. This is like about how the distance between the 2 objects. So this is when the objects are close, this is when they're far, and then these are kind of in between. Okay, and so when the objects are close, when you have a low noise level, then your non-collision probability, that's a plot of the non-collision probability, this is small, right? So if they're close to each other and you have very precise measurements, then you can tell that they're not safe, right? So then the non-collision probability is small. But as the noise in the measurements increases, so does the non-collision probability, right? And in all of these cases, the same thing happens, right? As you increase the amount of noise, then eventually you would conclude that the satellite is safe, even if it's not. Right, so here's a case where it's not safe. Here's a case where it's borderline safe. If the noise level is high enough, then eventually you just think it's safe. Right, so this is that notion of kind of this probability dilution, and there was really no explanation for this. So we thought about this, and it seemed to have something to do with, I guess, this kind of considerations that I'm describing here. And so actually we came up with this notion of what's called a false confidence phenomenon, false confidence property. And so what this basic definition is, that this is hypotheses tending to be assigned high probability, even if the data don't support them. So that's really what's happening here, especially this one, is that the data actually don't support safety of the satellite, but at some noise level, you could end up thinking that they're safe. So this phenomenon that's happening in that application is actually not special. So this is something that's always happening. It's a little bit hard to kind of piece this together, but in fact, this is all these bad hypotheses, these problematic hypotheses are always there. And so what this false confidence theorem says is that, well, give me any kind of a probability distribution that's assigned, that's defined on the parameter space. It depends on data, of course. So then I can always find some hypothesis for which that sort of bad thing in the validity property definition happens, right? So I found a hypothesis that's false, but is assigned high probability with some degree of frequency, right? So if I'm talking about probabilities, then I can't be sure that I'm not somehow assigning them wrong. I mean, it's not for every hypothesis A, it's for some, it's an existence result. But remember, the validity property was about for all A. So if there's some A, and it's not as if these are rare, there are lots of these problematic hypotheses. So this is, I mean, this is the reason why we need to think beyond ordinary probability if we're concerned about those systematically misleading conclusions like Reed and Cox mentioned about. Okay, so in some sense, this is not a surprising result. I mean, probabilities simply are too precise. They tell you how to calculate the uncertainty for every single thing. So it makes sense that data is just not that informative to be able to support, reliably support at least that level of precision, to be able to assign precise probabilities to every kind of claim that you might make about these unknowns. So the example I like to keep in mind is that if we were estimating a mean vector, let's say, okay, data is very informative about a mean vector. But if you consider some kind of a weird function of that mean vector, by example of a weird function, maybe like the maximum of the entries in the mean vector, you'd have a much harder time to estimate this object. The probability distribution is still going to assign a precise probability to hypotheses about the maximum in the mean vector. So it's still going to give you an answer. It's still going to be as precise as any other probability would be, but somehow it's not as reliable. So somehow there must be a price that's paid for trying to assign these precise probabilities everywhere. And I think that's what this false confidence property is doing. So when I talk about imprecision and the non-additivity related to that, what we're talking about is just sort of backing off our how committal we are, where we're taking sort of we're not willing to say, I'm sure that this is what the uncertainty, this is the degree of uncertainty that's there. I'm less committal. And so by being less committal, I can actually lower my risk of being wrong. And that's what allows us to avoid the false confidence phenomenon. Okay, so it's not just any kind of imprecision that'll get us there. And so that's the next part is, so what kind of imprecision can help us to avoid this false confidence? So here's just some, these are just definitions here, but so this, the lowercase pi, this is a regular function that takes like points in the parameter space to interval 0, 1. So not a function of sets now, it's just a function that takes in regular points and returns a number between 0, 1. And the condition that it satisfies here is that there exists some point in the parameter space that makes the function equal to 1. So here are a couple of examples of these kind of lowercase pi functions. One is kind of nice, right? It's up, up and then down. This one is not so nice. It goes up and then down and then up again. Both of these are fine examples of this thing, what's called a plausibility contour. So then what do you do with this? So this thing is kind of like the building block for a non-additive capacity. And so how you build this thing is through this supremum operator. So the way you assign these upper probabilities to these hypotheses is by optimization. Okay, so you have this function here, and then if you maximize that function over the set A, that gives you some number. It has to be between 0, 1. It has to have this kind of monotonicity property as well, because if you expand the set, the supremum can't get smaller, right? So this thing would define a capacity, and it's actually a very special one. The reason it's special is because it's completely determined by this regular function, right? So it makes some kind of an analogy to like a probability density, right? So probability density, we can take that thing and we integrate it, and that's how we define probabilities. This one is defined in a different way. You define it using optimization instead of integration. Okay, so this special property is called consonance, and the object that comes out of this also has another name. It's called the possibility measure. These are non-additive things. So these possibility measures are non-additive. You can do a quick calculation just by looking at the picture. So maybe if we considered a set A is like from 3 to infinity, right? So maybe imagine this line 3 that's there. If I know that this is decreasing, so the maximum would be achieved at 3, right? So that looks like maybe around 0.2 is the value. So that would be my upper probability assigned to this set interval 3 to infinity. If I do try to look at the other side, so the other side would be the lower probability part, I use that duality formula. So this A complement would be minus infinity to 3. That supremum would be 1. And then I do 1 minus that would give me 0. So I see here that my lower probability would be 0, but my upper probability would be like 0.2. So these are definitely non-additive objects, and that's not special to this example. Okay, so this is one way that you can imagine sort of cooking up one of these kind of non-additive capacities. So what does this have to do with statistics? If we think about the way we construct these frequentist procedures, very often they go in this way. And I guess in some sense, they only go in this way, which is part of my the third result I wanted to present. It says that you think about some function that takes the data and generic values of the parameter. And if the function should be such that, well, it returns maybe some small values when the y and the theta disagree in the sense that y doesn't really match the p theta that corresponds, right? So this is basically like you look at the data, you look at what you would expect the data to be if the theta were actually the parameter value. And if they disagree, then you assign some small score to that. If they agree, you maybe assign a large score to that. This is what p-values do. And so the key property here is that if the data come from this p theta, then when you plug in that value theta to this function, it has a uniform distribution, right? This is really the key property to p-values. There's nothing here really about a specific type of test, but this is the way we construct all of these things. So now the claim here is just, well, take that function and then think of it as one of those plausibility contours here, right? So then I can imagine, okay, I could construct this kind of an inferential model based on this procedure, and that's what I wrote here, p-value plus consonants. You could have also tried to construct a probability distribution out of this p-value. That's not something I would recommend, but this actually is provably not valid. But if I do this p-value plus consonants, then validity does hold. And so here's what the theorem says, is that as long as the p-value satisfies that condition, which was about this supremum business, which is not, this is not a real condition. It's basically always holds. So as long as it holds, then I can define my inferential model with this, this upper probability here, and then it achieves this validity property. So I didn't really have to do any work for this. I already know how to do these p-value kind of things. I just interpret it now as a piece in the definition of a inferential model with this kind of consonance property, and then I get the validity property that we were hoping for. Right. Actually, there's a stronger property here, but I don't really want to talk about that. But it's actually stronger even than the validity property that I've written down before. It's sort of uniform in those assertions A. So here's just a quick illustration to kind of see how this goes. And this is partly why I emphasize this part about that the validity property should be something that's related to, or that somehow is controlled for every A. So I think reason why I think this is important is that we often want to do certain kind of marginalization, and the marginalization may not be something that you would want to necessarily specify in advance that like, this is the only thing I care about. And so here's one example of this, is that it's a super simple type of a model. It says, well, I just have a bivariate normal, a theta 1, theta 2 vector, and an identity covariance matrix. So super simple. Two ways that you can imagine trying to construct an inferential model here would be, one is just, this is actually the fiducial distribution. This is a Bayes posterior under non-informative prior. This is one way you might consider to construct one of these inferential models. Say just take this is essentially a posterior probability to be normal, centered at data, same covariance structure. Okay, so another way to do it would be, you can do a kind of a sort of a p-value calculation that's specification through basically like the y minus theta norm squared. So that's effectively what I'm doing here, but that's not so important for this calculation. So these are two objects one can define. There's an additive capacity, and there's this non-additive one. And so now suppose that I say, okay, I'm not interested in theta 1, theta 2 specifically, but I'm interested in the ratio. So I see lens here. This kind of problem is related to some of these measurement error kinds of things in regression. So if you have measurement error in covariates, often these kind of ratios are things that can turn up. So suppose I'm interested in a hypothesis or like this one that says, the claim is that the ratio is less than 9. So I can specify this hypothesis, and maybe I'm interested in trying to quantify uncertainty about that. Now maybe it happens that the true values of theta is 1 and 0.1, right? So then that means that this ratio is 10, and then the hypothesis is false. Okay, so what we would like to see is that we don't want the things to be assigning high probabilities to false hypotheses. So here's I did a simulation. So this is where this is the setting. And so you look and you see, okay, well, the CDF for this, the probability, the additive one, right? So that's this black line here. So the CDF means that this is kind of where those random variables are sitting. And you see that they're always bigger than 0.8. So this is assigning, every single time is assigning a large probability to this false hypothesis. So this is where you'd be making some wrong conclusions. If I do this using this, this other kind of thing, it's not efficient. Right? The line actually corresponds to being efficient, the diagonal line. So it's not efficient, but it's not wrong. Right? So that's the advantage, is that by being not as committal, I can maybe not be quite as efficient, but I'm also guaranteed to not be wrong, at least systematically. So this CDF being above means that my this lower probability is not big, at least not too often. Right? So that actually is the, being above this diagonal line means that it's valid.
About 5 minutes left.
Okay. All right. Well, 5 minutes. Okay. So I suppose I don't have time to really get into this part. This is kind of I guess the sort of converse. And well, how about this? I'll just kind of skip over this, and if somebody wants to ask me a question about it, then I can come back. So this provides a sort of a converse to the previous result, which says that if you can construct this thing using the this consonance property, then you get valid inferences. And in fact, if you construct the frequentist procedures based on that, then they have the usual kind of frequentist control of the error rates. So I do think it's worth to maybe mention here sort of the takeaway message, even if I didn't get a chance to exactly write it, because I have a few other things I want to say here. Okay, I am actually going to skip this. Hopefully you'll ask me about it and I can get a chance to come back. So I do also want to say sort of how do we construct these things directly? So what I didn't get to describe was sort of an indirect way that these things can emerge. And so it would be interesting to ask, is there a direct way to do it? I think I don't have apparently so much time. So I think what I'll do is maybe just mention a couple of these things. So I didn't plan to say many details about it anyways, but so there's 3 things that I'll mention here, and then only at really superficial kind of level. So one construction is actually what's in the book of mine. So then how this one is actually working is a very specific type of construction of this inferential model, and the very first of these kind of validity theorems. And this is actually directly using those random sets like I described. I had those sketches at the beginning. So this is really directly using these random sets for the construction of the valid inferential models. So this has I think some nice, there's some benefits to this, and actually these random sets are actually very special, and I guess special in a sense that I didn't realize at the time, but more recently have discovered. So I did want to emphasize this one because I talked quite a bit about that plot from before. So in this case, this is where I've shown you the black lines would do the same as before. The red lines here are new. These are the lower and upper, like, belief in plausibility based on the techniques in the book here. And so what you can see here is that what's kind of the effect of the non-additivity. And so as you see the same kind of increasing the noise level, it's not as if it only goes up or only goes down. It's that you have these 2 pieces, and the 2 pieces do this kind of complementary thing where as the noise increases, what increases in terms of your uncertainty quantification is the imprecision, right? This gap between the lower and upper things is getting wider, which says that I know less. I have less precision in my measurements, so therefore less precision in my conclusions. So this gap is sort of like a don't know, and as the noise gets bigger, you don't know more. And so you're making less committal type of conclusions here. And so what I noticed this when I was preparing the slides is that, we think about that posterior probability here, or this non-collision probability here is, we think of it as precise in the sense of being like corresponding to some additive probability distribution, but the fact that it traces almost identically this kind of plausibility actually says that whatever this precision that was sitting there inside of the inside of that probability is actually, I guess, in some sense artificial, because it's not actually behaving like a probability, it's behaving more like one of these plausibilities. I don't know if that's a general type of thing or not, but that was something I observed here. Maybe I have a chance to talk about this one in case there's some questions, but interesting consequence of this theorem, which I didn't get to tell you about, is the proof is constructive. So that actually gives you a way of actually building these things kind of in a sort of a sneaky way, I guess I'd say. And it's a lot like this Rao-Blackwell theorem that you learn in the intro stat course, which says like, if you start with maybe you have an unbiased estimator, it maybe isn't a very good estimator, but it's unbiased, then the Rao-Blackwell theorem tells you how to make it better, right? You do that using the conditional expectations. So this is similar in spirit. It says if you start with some kind of a given procedure, then the proof of that theorem that I didn't get to talk about actually tells you how to construct one that's better. And so the output of this sort of an algorithm or the input is something, right? You take as maybe like in this example, it's the Klopper-Pearson confidence interval for a binomial success probability, which we know has the right kind of coverage, but it's not super efficient. So I can crank that Klopper-Pearson through the algorithm, the proof, which is now acting like an algorithm, and it spits out something which is actually better than what you started with. It's better in the sense that it's narrower type of contours here, which means narrower confidence intervals. This one requires a bit more time, so I'll save that. If you really want to hear about my power function for this mixture model, please ask at the end. So I made a claim at the beginning that I think in some sense there's some confusion about kind of the differences between frequentists and Bayes, and that this actually creates some kind of problems. I mean, the fact is that when we're dealing with this inferential output, whatever it is, this is not going to be straightforward. And so there's this feeling that the Bayesian interpretation is easier, or is better in some sense because it's easier. And it's easier because probability is familiar to us. And I think that frequentist often feels harder, but my claim would be that it feels harder because the things we're talking about, we don't understand mathematically. So I think this is important because now the theorem that I didn't get to tell you actually says that these p-values are plausibilities and that confidence regions are sets of sufficiently plausible parameter values. So I think this is the right way to explain these things. I think it's the right way to interpret them. And so this is actually how I teach. So this is what I teach the students in the class about this type of interpretation using plausibility. So maybe there's some students here who know, who have been there and heard these explanations. I have a biased sample of size 1 of feedback from a particular student who sent this to me after the class was over. She apparently had a successful job interview and wanted to tell me about it, and actually also to say that somehow this different perspective on p-values was helpful somehow during her job interview. I had some things here about computations, which I maybe should skip, but the reason I wanted to mention this was because I guess that maybe some students are here and are maybe interested in some kind of problems, right? This is a computational problem, but one that's I mean, maybe it's easy, maybe it's not, but I guess this is completely open domain because at least in terms of what statisticians are doing, we're thinking about something very different here, but the techniques are familiar ones. So things like Monte Carlo and optimization, this is all part of that plausibility contour type of evaluation. And so being able to do this in complex high dimensional problems would be important for this to ever really take off. So I think that could be an interesting and potentially challenging research problem. I have to mention here, so Brian talked the other day about conformal prediction and this plausibility. And so this is actually one of the things I've worked on recently. And so Leo will be actually defending his thesis in a couple weeks. So the part of his work was actually kind of fleshing out this connection between the conformal prediction and the plausibility stuff that I was describing here today. So there's a new version of the paper is there at the link below. In terms of what's next, I don't really have a whole lot of time to say anything about this, but one thing I do is I talked about this at the beginning, so I'll touch on it again. Actually, I didn't talk at all about the spectrum. So I mentioned this idea of the spectrum and somehow to kind of connect what is frequentist and what is Bayesian in some kind of a meaningful way. I didn't tell you anything about that spectrum. It's partly because I don't know, but partly because I think the most important part is to put the frequentism on the spectrum. If there's no way to see somehow the commonalities between what the frequentist output is and what the Bayesian output is, I think there's no chance of actually being able to draw the spectrum to sort of connect them in some meaningful way. So the connection that's here in terms of frequentism being represented as imprecise probabilities and Bayesian being represented as precise probabilities, this creates an opportunity to link them. And so I'm particularly excited about thinking about this notion of partial prior information as sort of being able to, what would show up along that spectrum in between. So things that we do things like structural assumptions, maybe like sparsity and some kind of like high dimensional parameters. When we think about models, we're very often saying, okay, I prefer models that are parsimonious, Occam's razor kinds of things. So these are assumptions that we're making, but in some way you could think of them as kind of partial prior information. And so how could you incorporate those things in a more formal way and somehow land in between these two Bayesian and frequentists kind of on the spectrum while still being both valid and efficient? So that I think is it's kind of the main focus that I have, how to kind of understand this spectrum and put it into practice. So I'll say here just, I think this is a new and exciting territory. And in case, so imprecise probability probably is something that you're not familiar with. If you wanted to know more, I thought I have these books here and I was going to write just the names, and I thought, well, this is probably a better way. So I stacked them up and I took a picture. So here are 6 books that I own that I think are relevant to imprecise probability. These are really the books. So this first one here is a seminal work. This was Glenn Schaefer's, actually came out of his PhD thesis. So remember, Glenn Schaefer gave a talk here that was earlier this semester, I think back in January. So he's of course very involved in this area. He's really wrote one of the first books. Yeah, by the way, these are in chronological order, 76 all the way up to 2021. So I just got this one. It's a monster. I think, I don't know if you can see, it's like 700 pages of things, but yeah, excited to get a look at this one, Fabio Kuzlin. Okay, and so I'm well over time now. So I say, well, thanks for your attention. Emily mentioned at the beginning something about Researchers One. So I know a number of you joined for the COVID panel a few weeks back. So thanks for that. A new thing that's coming up, actually related to the topic from today, there's a whole imprecise probability community, mainly in Europe. So actually Researchers One is going to help them running their virtual conference this summer. So I'll have some announcements about this, but this should be in early July. Yeah, so that's all I have, I guess, unless there's some questions you'd like to ask.
Thank you very much, Ryan. Yeah, if there are any questions, now's the time.
Actually, could you go and explain some of the stuff you were going to say on, I think it was slide 21. I feel like that helps put stuff into context, maybe.
I missed that one part.
I think it was slide 21.
Okay. Yeah. So the idea here was what I hope to be able to do is to say that there's no things that are frequentist that don't fit into this imprecise probability type of framework. So we saw that I can take the imprecise probability things, in particular these inferential models with this consonance property. I can get good frequentist procedures out of them, but I need to, if I want to be able to say frequentist is on the spectrum, I have to somehow be able to go the other way. So this one, the first thing that we showed was, okay, these things with the nice kind of consonance property, they are nice frequentist procedure, correspond to nice frequentist procedures. So to put it on the spectrum, it needs to go the other direction. I have to say that really anything that's a good frequentist procedure can be represented as one of these like consonant inferential models. Okay, so the hard part is that who knows what's in here, right? This is really, you can do any kind of thing you want, and if as long as it has good properties, it sits there. So there's really no common structure in some sense to those objects that are sitting in this thing that are quote frequentist methods. And what the theorem here says is that if you give me some confidence regions, so a family of confidence regions, these are indexed by the confidence level. Now these can be confidence regions for, they don't have to be for the full parameter. These can be for some marginal, some interest parameter, some function of the full parameter. So think about like the student T confidence interval. This is a confidence interval for mu that doesn't say anything about sigma. Okay, so lots of these things like F tests that we do, these are things that are always about one component, mostly about one component of maybe a larger set of unknown parameters. So I can take these things can be for any of these kind of a feature of interest. And the requirement is that they achieve the coverage probability, which is this first part. Otherwise, they're not really confidence regions. Second is that they're nested. So that just means that if you have lower, or let's say higher confidence level, the set's bigger. Right? And then there's this other thing, compatibility, which is too much for me to really explain here. I did put one comment. It's great grammar, so I'll share that with you, is that I don't know of any not weird examples where this fails. So then what's the claim here? So the claim is that, so I take as input these confidence regions, and then as output, or not necessarily output, but that I can identify one of these inferential models that's valid, and it's an inferential model for the entire parameter, not just for this interest thing. And the structure that this inferential model has is one of those consonant things, like a possibility measure. And then what's so good about it is that, well, if I were to extract the corresponding marginal plausibility region for this phi, the thing that I'm of interest, then it's actually no bigger than the one that I started with. Mm-hmm. So then anything that's the takeaway here is that anything that's, if you start with something that has these sort of good frequentist properties, then at the back, I find, well, it's just one of these inferential models that has this consonance or sort of possibility measure type of structure. And it's actually at least as good, maybe even better than the one that you started with. Mm. So this is like this kind of, it actually sometimes is a proper containment. It's not always equal. In some cases it is equal, but often, in some cases at least, this is a sort of proper subset. And so that's actually what was in this picture here was the black line is sort of all the way tucked inside of the gray line. So the gray line is kind of like a visual description of the Clapper-Pearson confidence intervals. And then this is the that kind of contour function that comes out of the proof.
So the arbitrary frequentist procedure would have to admit a full like confidence set, right? It couldn't be like you have like the MLE and then it's not clear what the confidence set would be.
That's right. So what I mean by a frequentist procedure is like a confidence region.
Yeah, okay, right.
So like an estimator is an estimator, but if I'm trying to somehow quantify uncertainty, I would do that in the frequentist way, which would be with the hypothesis test or with a confidence region, something like that.
Mm-hmm. Yeah, and it gets even a little bit more complicated because a lot of those just adhere to some sort of asymptotic theorem about like where that confidence region would go to, I guess, right?
I think what you're asking about is the I guess things that are asymptotically
it's like we usually like plug those in the place of not having a closed form or the finite sample result. So there's even like this one layer, I guess, removed. But yeah.
Well, yeah. So right now, this is talking about a fixed sample.
Right.
I mean, there's, I guess, the sort of natural intuition is that if you achieve this approximately, then in some sense, this must be approximate. I haven't investigated that at all. The first step was to say, if this is actually a frequentist procedure, like it does have the frequentist property that it's advertised to have, then can you describe this thing using the imprecise probability framework? Well, since you gave me a chance to talk more, I'll say a little bit about this picture here. So Larry Wasserman actually came to give a talk. This was BC before COVID. He was actually in SAS and did a regular seminar. It's hard to even remember when that happened. And so one of the things he talked about there was a thing he's calling universal inference, which is basically it's a kind of a tweak on the usual kind of likelihood ratio tests. But that achieves like guarantees, it guarantees nominal, in this case, type 1 error rate control. So they have one example in the paper, which is about testing mixture model. So it's basically to test one normal distribution against a mixture of normals. And I don't really know for sure, but my understanding is that this is a very difficult problem. I know a little bit about that, but that essentially, as far as what they said in the paper, was that there are no procedures besides theirs that have guarantees in terms of the size, like the type 1 error rate control. There are other tests, and those tests are fine, but they don't have this like guarantee. So what I did, I took their method and I cranked it through this kind of algorithm that comes out of the proof. And then, so what the argument would say is that thing that comes out of the proof can't be less powerful than the given one. So they could be the same, but it can't be less powerful. And so what you see in this picture is a plot of that power function. This is the Wasserman's thing based on this, what they call split likelihood ratio test. And this is the power function for the output of this kind of like inferential model algorithm. And so it hits the 0.05 here like it's supposed to. That's because it has to be valid, but it's also more powerful than the split likelihood ratio test in this example. So I think that this is basically the only example I've done. I did one other example of this, which also was, I think, pretty interesting. But so I think that there's a lot of opportunities to kind of think about this in this kind of Rao-Blackwell type of way, is that think of these procedures as starting points, and then you crank them through this algorithm to make them more efficient. Mm-hmm. And I don't know what would happen with other cases, but this is one that I've looked at. I thought this was a nice illustration.
So thank you very much for the talk. I think we'll wrap up here, but if you do have any follow-up questions, I'm sure that Ryan would welcome them by email.
Yeah. I can also sit here for a while. I don't know if, I think I'm the host. So if there's other questions, I'll sit here for a while if you want to ask. If not, you don't have to.
I have another meeting, but I will send you an email because I had another question. So
okay, cool.
Okay. Thank you very much. Great talk.
I don't know.
Thanks, Ryan. I learned something here. Whenever I'm stuck, I'm going to talk about that theorem that I didn't show anyone.
That is a good technique. Yeah,
that's a good one. I will ask. Go back to page 14. No, wait a second. 14. Yeah. Or slide 14.
Yeah.
Okay. I didn't quite understand that last phrase. Noisier data makes. Does that bias the calculation of probability, or are you? And what do you mean by noisier data? Is it just noisier measurements of something that's true, or these are satellite paths that are just wiggling all over the place?
So you could think of it in like, so it's like there's a quantity that you want to estimate. And then so this is basically, you can think of it as like this, like if in a normal distribution, for example. So like you're trying to estimate the mean, but then there's this other kind of like the sigma is also there. So you have a mu that you want to estimate. There's a sigma that's there. You maybe know what it is, but the larger this thing gets, so that's like, it's becoming more noisy. So it's like the thing that you're trying to estimate is the same, it's fixed. And then you just have more and more noise in the observations. So they're kind of like a sort of free parameters in this sense. So as what happens in this context is that the things are really far away and they actually have lots of data, but because of the kind of the magnitude of the things that, these distances and stuff, so there's a lot of just sort of inherent variability that's inside of these measurements.